Welcome to part 3 of 3.4, the very last part of this lecture. I'm Miss Coco, your host, once again. And in 3.4, I just want to do a really quick overall summary. We are talking about related conditional statements, things like taking if P then Q, or P implies Q, as this statement says right here, and finding the converse and their inverse and their contrapositives. So we're applying those, and we're also talking about alternative common translations of if P then Q. The last part 2 video, we left off with example 3, rewording conditional statements, meaning we were taking words like you'll starve if you don't eat and putting in an if P then Q based off of what it looks like in this chart. Now we're going to do, for example 4, we're going to take if P then Q, excuse me, I already wrote something here in practice. We're going to take if P then, we're going to take a sentence that we are given, such as this one in part A, and we're going to turn it into symbols, which is what we've been doing, but now it's a little bit different because if you notice, for part A, this says, a triangle is equilateral if it has 3 sides of an equal length. Well, my question here is before this if word right here, which of these is P and which of these are Q? Well, how I would attack this is first, I would identify any connecting words or any words that kind of are a buzzword that might be similar to these words up here in the chart. So for example, this is if then, and if P, comma Q, if P implies Q, so implies only if, and so words like this that are kind of like helping us see the form of the sentence. And what I mean by that is if you look at this sentence right here, and I circled the word if, to me this kind of looks like there's a form, and this could be, this first sentence right here looks to be a statement, right? And the second sentence looks to be a statement too, before and after the if statement. So when I look up here, I see that Q if P. Well, to me this is saying that this first statement is Q, and the second statement is P, which is exactly what they tell us in the directions. P is a triangle that is equilateral, and Q is a triangle that has 3 sides of equal length. So that makes sense. So, like this says right here, our last step, once we identify all that, is to write our Q implies P. And this is your answer. For part B, we have a triangle is equilateral only if it has 3 sides of an equal length. Well, right here, we know that a triangle is equilateral, so this is P, and only if is that buzzword that I was talking about, so I'm going to look up at my chart here in a second and see what the style looks like for that. And then after only if, we have it has 3 sides of equal length. And I know that that statement right there equals Q. So let's see what this looks like. Only if, when we look up at our chart, says that P, I keep meaning to hit the highlighter, P only if Q. So that means that P goes first, right here, and implies Q, which is the second. So this is our final answer. And that's how you turn these words into symbols. The next thing we're going to talk about is biconditionals. And biconditionals are super fun. They look more intimidating than they really are. But they are actually really, really fun. And give me a second. I'm going to take a drink of my coffee. Good stuff. All right. So biconditionals. The compound statement P if and only if Q, often abbreviated as PIFF, and you always say if and only if, is called a biconditional. It's symbolized by this P with the double arrow in the middle and is interpreted as the condition of two conditionals, meaning P must imply Q, and this is your conjunction, this is your and, Q must imply P. So what this is telling me is that you have to look to see if both ways are true. So you have two conditions and you have to look both ways. So you're actually looking at the converse. Because if you remember, the converse is where they just flip things around, right? So what you're looking at with biconditionals is you're looking at, You're looking at the original conditional statement to see if it's true. You're going to say, and you're going to take the intersection and see if its converse is true. And then you're going to be able to tell whether or not the entire statement is true. So that's how you think about these. And remember, this is what it looks like when you're trying to create a truth table for it. This is the end result. So P, if and only Q, is congruent to P implies Q and Q implies P. So that's the big theorem right there. All right, so you're probably asking me, Miss Coco, how do we decide whether or not these are true? Well, it really depends on what you're given. We're not making truth tables for this, but you could make a truth table. Actually, you are going to make a truth table. I would highly recommend making a truth table to see what this looks like in all cases. So pause your video and create a truth table for this statement right here. Truth table. Yeah. I don't know why I just sang to you guys, but got to keep math interesting, right? So pause right now. See if you can create a truth table for this side of the statement. All right. So one of the things that you're going to be asked to do is this objective right here. Example 5, determining whether biconditionals are true or false. Well, let's look at it. We're asked to determine whether each biconditional statement is true or false. And this is something you're going to do in your My Math Lab, and I'm going to teach you how to do it. So I'm going to go ahead and add an extra piece of paper here so that we have a little bit more room. We want to know if 6 plus 8 equal to 14 if and only if 11 plus 5 equals 16. Is this true? Well, first, we are going to identify our P and Qs. So first, we know that before the statement, because it's P double arrow Q, that P is equal to 6 plus 8 equals 14. And we ask ourselves, is this a true statement? Is P true? And 6 plus 8 is 14, so yes, we can say P is equal to true, or T. So I'm going to box that out. Next, we're going to do the same thing with Q. We know that if this is P right here, then this is Q. So Q equals 11 plus 5 is equal to 16. We ask ourselves, is this true? And we're going to say yes. Q is equal to true because 11 plus 5 does equal 16. Our second step is we're going to sub P and Q into our P if and only if statement, which we know is congruent to P implies Q and Q implies P, because you have to look both ways here. So what we're really going to do is we're going to take this and sub our P and Q. And when I say sub, I mean the fact that they're both P equals T and Q equals T. So let's see what that looks like. I'm going to change my color up here. So here we know P is true, Q is true, and we know that Q is true, which implies T for P because it's true as well. So we analyze this from left to right. When when the antecedent is true and the consequence is true in this first statement, the overall statement is true. I'm going to bring down my intersection. Same thing, I'm going to look here. I know that's true. And then I know that in order for these both to be true, this statement to be true in an intersection, because remember this is and, which means intersect. I know that they both have to be true, so this statement is true. So the logic is true. Woohoo! And I'm going to do one more for you all. I'm going to do this one a little bit faster. I have my first, I'm on part B here. My first statement is P. Change this up. P is equal to 6 equal to 5. Is that true? No. P equals F. And I know that I have Q is equal to 12, not equal to 12. Is that true? No. Q is equal to F. My second step, it's an if and then only if statement. So we have P, if and only if Q, which I know is equal to P then Q and Q then P, because we got to look at it both ways. And I'm going to sub F implies F and F implies F here because they're both false. I know that when I look at this statement, remember this is a conditional statement and there's only one case where it's false, and that's the case where you get lied to. So this becomes true, and this statement is true as well. So the overall T and T, because remember this is and, is true. So this statement is true. Pretty whack, huh? Yes, these can be whack. So that's why I say don't really look at the words. All right, because you're like, Miss Coco, but 6 equals 5 if and only if 12 doesn't equal 12. And that doesn't make any sense because those are both false. How do we have a true statement? Well, in the world of logic, in class we'll discuss a little bit more of this, but it's really kind of funny sometimes. All right, so the very last one is Mars is a moon if and only if Jupiter is a planet. Well, this is P. I'm going to do this one faster. Mars is not a moon, so this is false. We have if and only if, which is that arrow like this, if Jupiter is a planet, and this is Q, which is true. Mars is not a moon, so that's false. Jupiter's not a planet, so that's true. And then we know that this is if and only if, so we are going to plug our P and Q into this statement. So P is false, and it goes to true. Q is true, and it goes to false. So here we have, I'm going to bring this out so we don't look at this other stuff down here. So now we're going to analyze the logic here. The antecedent is false, so it doesn't matter what happens to the consequent. This is just true. And here we have the lie. True goes to, it implies false. Remember, If you eat your dinner but you don't get your dessert, you're lied to, so this is a false statement. Once again, we have an intersection, and in order for an intersection to be true, these have to both be true, so this automatically defaults to false. So this is a false statement. So when Mars is a moon, if and only if Jupiter is a planet, it is false. And that is it for 3.4. We'll talk more about this in class, and I will see you later. Bye.